know, the idea is that up to now, we've really just estimated a single combination of parameters, the most likely one. But of course, just because one particular combination of values is most likely according to our, you know, our sort of noise model and so on, doesn't mean that other combinations marginally separated are wrong. They're just, you know, slightly less likely according to the way that we've constructed our objective function. And it's very often useful to be able to identify the kind of range of parameters in addition to the single most likely, the range of combinations of parameters that are plausible given the data that we've measured. And there are various ways of doing that. So one kind of common idea, which I'm sure you've all come across, is the idea of confidence intervals. So we might express a standard deviation, for example, on each of our different parameters expressing how the likelihood of the parameters varies as we move away from the maximum point. And more generally, we might try to reconstruct a full picture of the posterior distribution on those parameters. Let's just dwell on those two ideas for a moment. Think about confidence intervals, first of all, very simple concept. So a very common confidence interval that you see used in lots of contexts is the idea of a 95% confidence interval. So just thinking in one dimension for the moment, if we can assume some kind of, you know, symmetric Gaussian-y kind of shape of the likelihood function around the maximum point, x tilde, maximum likelihood estimate, or maximum or posteriori estimate, then the 95% confidence interval is the range around there that contains 95% of the mass of that posterior distribution. So you just cut off.
Can I see your iPad, Danny?
Oh, sorry. Yes, thank you. There we go. So I've just drawn this distribution. So let me draw it again. Start again so you see it. See the construction. So let's suppose just in one dimension, we've got a nice symmetric likelihood distribution for P of A given A. I'm going to use P of X given A and P of A given X interchangeably throughout here on the assumption that we've just got some broad uniform prior. So let's suppose that that distribution has quite a nice friendly symmetric shape around our maximum likelihood estimate x tilde. Then the 95% confidence interval is the one where we simply chop off the top 2.5% of that distribution and the bottom 2.5% distribution remaining, and take the bounding the 95% of the mass of that distribution. If we can assume that distribution is Gaussian, then that 95% confidence interval corresponds to the 2 sigma range, where we take plus 2 sigma and minus 2 sigma from our maximum likelihood estimate, and that gives us, again, approximately 95% of the mass of that distribution. There are other corresponding distributions. So if you take just 1 sigma, for example, that contains something like 66% of the mass of that distribution. And if you take 3 sigma, that contains 99% of the mass of the distribution. So those are kind of common intervals. If we can assume a sort of nice symmetric shaped posterior distribution. If we can't, then the 95% distribution and the 2 sigma distribution, actually 2 sigma range, depart from one another somewhat. So suppose, for example, we've got a kind of more skew shaped likelihood, something maybe more like that, the sort of thing that we thought about when we were considering our sort of log measurements in diffusion imaging. Now, of course, the 95% range is still quite sensible. Chops off, you know, maybe that top and bottom 2.5%, giving us a, you know, a range that encompasses the central 95%. Whereas the 2 sigma range goes a bit weird in these situations because, you know, the maximum likelihood estimate is here. And, you know, sigma is probably something like, or 2 sigma would have a, you know, a length, something like that maybe. Which sort of, you know, the 2 sigma range then around the maximum likelihood estimate isn't, you know, is less useful in that kind of situation because it includes this kind of very low probability range here and excludes this quite high probability range here. Nevertheless, you know, these are sort of common ways of constructing confidence intervals. What we're going to focus on here is a bit more the latter idea, reconstructing the full posterior distribution on X. Let's just kind of remind ourselves what that object looks like. So going back to our simple model from diffusion MRI, let's just think about that simple case to start with. So our vector of unknown parameters just got 2 components to it then, S0 and D. And so the posterior distribution, or equivalently likelihood, is a 2-dimensional function. Depends on the values of those 2 parameters. And so I'm just going to draw a cartoon one, not with any accuracy at all, but just to give a feel for what this object that we're thinking about looks like. So we might have one axis, which is D here, another axis, which is S0. And as we vary those values, we'll get different values for this likelihood P of A given X. And so we might end up with some function. I'm going to draw it as kind of contours, something like this. So we get some probability or some likelihood function like that, expressing the you know, likelihood of the different parameter combinations given the data. And our maximum likelihood estimate or map estimate is here, of course. We've got a little local maximum over here. But that's the object then, rather than just trying to find our X tilde here. Now we're starting to think about trying to reconstruct this whole distribution. The first of the 3 techniques for approximating the posterior distribution that I want to mention. And so the first of these is Laplace's method. Pretty simple idea. So actually, if you look up Laplace's method in general, it is a kind of general method for approximating integrals of complex functions. And the way it does that is by approximating that function as a series of Gaussian distributions. In our context, so Laplace's method again refers to the idea of approximating things with Gaussian distributions, but we are going to approximate the posterior distribution on our parameter estimates as a multivariate Gaussian function. So just to illustrate what that means, if we go back to my sort of cartoon posterior distribution here on D and S0. So what Laplace's method does then is approximates in the vicinity of the maximum likelihood estimate x tilde here, a Gaussian function that has approximately the same shape as the posterior distribution local to that position. So it doesn't worry about things far away like this local maximum. Just in the very local area, it does its best to approximate that function with a Gaussian function, i.e. a function that has these sort of elliptical contours. And of course, once we do that, once we've got that Gaussian approximation, very straightforward. Some familiar quantities like 2 sigma ranges or 95% ranges on each of the different parameters that we're interested in. So going back then to the slide here, so how do we go about doing that? So if we're going to approximate the posterior distribution as a Gaussian, we need to estimate two things, its mean and its covariance. So as I said, we're looking in the vicinity of the maximum a posteriori or maximum likelihood estimate. So we have that directly. Let's assume that we've already identified our maximum likelihood estimate. So the only thing left then to estimate is the covariance of that function. And the beauty of Laplace's method is that we can get an estimate of that covariance from a very simple expression. It maps directly to minus the inverse of the Hessian matrix of the log likelihood at the maximum likelihood estimate. Let's think about that for a moment. First of all, why does that make sense? Is there some intuition as to why we would set the covariance to the second derivative of this, the log likelihood? Well, I think it does make some intuitive sense if you think about it. The curvature, or the second derivative, is basically the curvature of the function at this point. So we're saying then when the curvature is high, the covariance is low, which would suggest, I think, that our confidence is high. Let's just think about that in one dimension for a minute. So suppose we've got a posterior distribution that has a very low covariance. So that would be something that's sort of very peaked, like a Gaussian distribution that looks like that. It's got a small standard deviation or variance. And if sigma is small, that would mean that our confidence is high. Confidence in the single value at the beginning is high. You don't have to move very far away before the likelihood drops off very dramatically. And because this function is very peaked, I think we'd expect that the curvature at the peak is high. The value is changing very rapidly. So I think it makes sense that high curvature maps to low covariance. And on the flip side, of course, if we take a very broad Gaussian distribution like that, so there sigma is high, confidence is low, because we can move quite a long way from that, from the maximum likelihood estimate, and still have quite high likelihood of being the right position. And there, of course, the curvature is low. Maybe just to give a slightly higher dimensional insight into that, let's think. Remember this. We thought about this little bit of the Lake District and trying to find maxima in this kind of terrain. So, this problem that I've just talked about, having high confidence, it's similar to, if there's a sharp, jagged mountain with a sharp peak at the top. Here it is. That's got, it'd have, if you climb up to the top of something like that, you're actually, you're pretty confident, you're at the top when you get to the top, because it's got a very pointy top, a bit like Cady Hill here. It's got very sharp sides, and the contours are quite close to each other when you get to the top. It's a little bit, a little bit not quite as dramatic, but a little bit like this mountain here. Whereas if you compare that to a sort of a hill that's maybe got a kind of a flatter top to it, something like that, a little bit like this Tabor Hill over here. You can see the contours are much sort of further spaced here. When you get to the top of a hill like that, it's much harder to know, I get to here, am I at the highest point? I'm not sure. It's much harder to identify, because the curvature is much lower at the peak than it is in this sharp, jagged mountain here. So that's sort of the intuition behind Laplace's method. Let's think about it slightly more formally. So where exactly does this, why exactly are we equating this inverse Hessian matrix with the covariance? Well, actually, it's fairly easy to see. If we write down the posterior distribution in the form of a multivariate Gaussian distribution, so we've got to call the form of it, it's 2 pi det sigma, isn't it? N over 2. So this is a sort of general form of the multivariate Gaussian distribution. So we're taking the mean as the maximum likelihood estimate. This is our covariance sigma. That'll be all over -2. Let's take the logs of it. So what we're looking for then is the second derivative of the log likelihood. So log of that is then minus n over 2 log 2 pi det sigma minus 1/2 x minus x hat x tilde transpose Okay, so now let's think about differentiating this twice. So we're going to have to doing a slightly complex operation here, differentiating with respect to the vector x. So if we just do it once, first of all, so strictly I should be doing this element by element of x, but actually, first of all, you can see that this term here doesn't depend on x at all, so that's going to disappear. And this second term here is, it's x squared times the inverse of sigma effectively, isn't it? And actually I can treat this as just x squared inverse of sigma and differentiate it accordingly. So that becomes, so we've got the -1/2 coefficient already. Differentiating with respect to a vector x of this pair of x minus x tildes will give me 2x minus x tilde transpose sigma -1. And then differentiating it again, I hope you can see that what we're going to be left with is just inverse of sigma. So this, of course, oops, write that out properly. d by dx squared of log px given a is minus sigma to the -1. And this thing here, of course, is exactly the Hessian matrix evaluated at the maximum likelihood estimate. And so that gives us exactly this relationship here. Okay, so that's how it sort of falls out of the Gaussian approximation to the likelihood. Okay, so pretty straightforward then to write down. But of course, implementing this doesn't look particularly straightforward. I mean, as we noted in the second section, when we were thinking about parameter estimation, computing these second derivatives of often quite complex and high dimensional likelihood functions like this can be quite an onerous task. But also, as we noted there, this of course is one of the quantities that some of those nonlinear optimization algorithms use to identify the next step in their search for the minimum of an objective function. And in fact, so common is it to want to access that Hessian matrix once the search has converged to its maximum minimum point, is that in almost all commercial implementations of these nonlinear search algorithms, there'll be a version of the algorithm that returns that Hessian matrix, precisely so that you can use it in methods like the Laplace method for estimating the uncertainty on the maximum likelihood parameters. So this is the help page for fmin-unc in MATLAB, and you can see here that there's a version of the function where you can get this Hessian back. Because it's computing it, at each iteration, it's no added cost for it to be able to return it at the end of the calculation. So that makes it, super simple to use Laplace's method in conjunction with things like fmin-unc. Just go back here a second. So let's just think about the contents of this sigma array once we've estimated it from the Hessian here. So going back to my example, what was it here? So for this two-dimensional example then, where we're estimating S0 and D, what would sigma look like? So it would have the following form, which is quite helpful. On the diagonal elements of sigma, so it'll be a 2x2 array, 2x2 matrix. The diagonal elements will be the variance of the D parameter and the variance of the S0 parameter. So directly enabling us to construct, for example, these 2 sigma, 1 sigma, 3 sigma ranges if we want to. And the off-diagonal elements are then the covariances of those 2 parameters, S0 and D, telling us about the orientation of the elliptical contours of our approximation to the posterior distribution. How are we doing? 10:44. Okay, one last thing I'm going to say, which is a kind of warning about the usage of Laplace's method. So it crops up in the coursework. In one section, I do ask you to use Laplace's method to estimate the uncertainty on a couple of estimated diffusion parameters. But quick question then. So suppose we, let me just flip forward one slide again to the MATLAB help page. Suppose, as we've suggested previously, to find our maximum likelihood estimate parameters, we give fmin-unc our old favorite objective function, the sum of square differences. And it happily finds the x tilde that minimizes that sum of square differences, gives us it back, and we ask it to give us back the Hessian as well. Is that Hessian the Hessian that we need? Can we just invert it, negate it to obtain an estimate of sigma directly? Just have a think about that for a moment. It's fairly obvious that the answer is no, or I wouldn't be asking the question. But why is it not quite the Hessian matrix that we need to estimate sigma? I'll just start working through a calculation and leave you thinking about that. The calculation will demonstrate why it's not quite the right thing and show you what is the right thing. So if we So first of all, what f min unc will return is the second derivative with respect to x of f of x. So second derivative of this sum of square differences. Objective function, so that's what it will give us back. However, let's remind ourselves where this sum of square differences objective function came from. Of course, it comes from our assumption of Gaussian noise and being able to write the likelihood of our set of measurements for a particular set of parameter values as this big product of Gaussian distributions, one-dimensional Gaussian distributions. I'm going to work through the same old calculation. Let's take logs of it, turn it into a sum. Of course, we need this log likelihood anyway. Oh, it should be over sigma squared here, shouldn't it? Okay, so what we want then for our sigma, going back to the previous slide up here, is the second derivative of this log likelihood here. Remember, we're treating that as the p a of x, a given x, as interchangeable with px given a. So we just want to differentiate that twice. Let's think about differentiating this function on the right-hand side twice. So I'm not going to go through the whole laborious algebra, but let's just think about what it's going to look like. Well, this first term here doesn't depend on x, so that's just going to disappear, isn't it? So I think we're going to end up with just the second derivative of the other term, the sum of the other term. Or rearranging it slightly, minus 1 over 2 sigma squared d by dx squared sum of square differences. Okay, so that's the, that's truly the second derivative of this log likelihood function. But how does it differ to what we actually get back from f min unc? That was this thing here. There is a subtle difference, but it's an important difference. And it's this factor minus 1 over 2 sigma squared. So we quite reasonably, when all we were thinking about was finding the maximum likelihood estimate, we quite reasonably dropped that factor because it doesn't affect the position of the maximum and it simplifies our objective function. But it does matter here because that minus 1 over 2 sigma squared factor affects the overall scale of this Hessian matrix, which is crucial in getting the scale of this sigma matrix correct. So to go back to my original question, the answer is not quite. The Hessian matrix that we get back from f min unc is this one here in the red box, this one here, but it's not quite the one we need to get the scale of sigma right, because we dropped this -1/2 sigma squared factor from the second derivative of the log light field, and we need to put that back to make sure that we get the scale right. Okay, so that's I won't say any more about that, but just bear that in mind when you get to the question about Laplace's method, that you need to make sure that you've accounted for sigma correctly in order to get an accurate estimate of sigma squared, of the big sigma.